Okay, let's get going. Okay, so we're going to skip over this because I want to get to some more interesting things, and if we end up having some more time. But there's also ways to accomplish this task with fold right and fold left that have better complexity. And fold right and fold left are very important, and so I want to teach them really quickly, but we're not going to do the implementations ourselves right now. So what I want to point out here is what actually happens when we run a fold right. So fold right takes as its first argument a function that has two arguments. And then it takes as its second argument a starting value. And then as its third argument, something that's foldable, in this case, a list. And really, the best way to intuit this is to see what kind of structure is actually built up as this is accomplished. So visually, you can see here kind of what's going on, but this is an even better visualization. And so the subtraction function is here, and then it gets two branches. And on the second branch, we have, again, a subtraction function with two branches, and then a subtraction function with two branches, and then a subtraction function with two branches. None of this, since Haskell has lazy evaluation, all of this has to wait for these two arguments to happen for this binary operator to have what it needs to simplify into a smaller form. And so from there on, that's why these inner parentheses actually are evaluated first. And so 4 minus 0 is evaluated, and then 3 minus 4, and then 2 minus 1, and then 1 minus. And then that ends up equaling with a minus 2. Fold right is often a little bit more difficult for people coming from strict or imperative languages to intuit over, because it really is not very useful in a language that doesn't have laziness. Because if you don't have laziness, that would mean that every time this expression was created, it would have to traverse the entire foldable thing and run the computation, which is very expensive, right? And so, but because we do have laziness in Haskell, actually foldar is often something that we want to reach to when we want to kind of stream over large collections of things. So to get an idea of the other option we have is fold left. So here, fold left works in a similar way. It also takes a binary operation as its first argument, and then the starting value and the foldable thing. And you'll see that it's nested in the exact opposite way as the fold right. But the structure gets built up the same. So we start building out the minus, and then we get 4, and then minus, 3, minus 2, 1. So here, the first thing to be evaluated is going to be 0 minus 1. And then the result of that will be evaluated with minus 2, and the result of that with minus 3, and then the result with that with minus 4, and then we're back in normal form. And so if you're ever looking at like a fold, either a right one or a left one, and you're starting to get a little bit lost, what I do is I just grab out a piece of paper and I just draw this little graph. And it makes everything easier. And sure, sometimes it's going to be a giant data structure, but you can always come up with a simpler version of the data structure that is just a lot smaller that will accomplish the same thing. And then you won't have to be thinking to yourself, what's going on here? Cool thing to keep in mind is that while there are considerations for performance that are associated with both of these and evaluation order, if you're folding over something that is monoidal or a semigroup, which means that it has or that the operation that you're using is associative in nature, then the ultimate value that comes out of the other end will be identical for both folds. So that's why in here I use subtraction to illustrate the difference, is because subtraction is not associative, and so there will be differences in output for either. But if we were doing this with addition or multiplication or any other associative operation, then the answer that came out the other end would be the same in both cases. So kind of a cool little tip. Okay, so we're going to move on to the Caesar cipher. So a few concepts to go over. So I'm just going to drop these in here and make sure that I think mostly we've covered these, but do some quick examples. So here, I'm going to go ahead and write this. I'm going to make a new file called caesarcipher.hs, and I'm going to be very careful about how I spell things this time. And let's see. And I'm just going to copy over the language extension here. And then we're going to have the module name. And I'm going to also copy over the import statements. Okay, so we went over before, but I'm going to go over them again. So what we're going to do is we're just going to create the name mode, and it's going to be a sum type with 2 data constructors. And we're going to derive show and EQ. And so then we are going to have secret message so that we have to with. And you can put whatever you want here. Maybe that for now. And then we're going to have some labels, also going to be a t.text. Oops. And I'm going to go over to my notes. And I'm just going to copy this. In fact, I'm going to leave out these numbers just to make things a little bit simpler. Oops. Okay. And so now we are going to have a couple of options here. So we're gonna divide this up into 2 things. We're gonna have an encrypt character function that takes in a mode and an integer and a character and returns another character. And then we are going to have an encrypt message that is going to take a mode, a key, and a message, which should be a mode. Don't forget those dots. A mode, an int, and a t.text. And it will return a t.text. And this is going to do a fold left, but we're going to fold left over text. And so text is foldable, but we're going to do so with the fold L that comes from the text package itself. And so then in here, we're going to need some kind of function that we're going to have to write later on. And then we're going to use an empty string as the accumulator value, and then the message that comes through the message, which is the original unencrypted message. And so what a function that can take in a and then over the taking in a character at a time and encrypting a character, building up a new if I did something, first thing that we want character function, encrypt character with encrypt and 1 and A, we would want this to produce a B. And so what's happened is that we've found the position of A, which is the input, inside of our symbols. We've incremented that position of 1 and by 1, and we've returned a new character, B. Three, 4, 5, and F back. For function, encrypt character, and which is here in the notes, is that we've got a text symbols of all possible characters. So look up the index of the input character in symbols, and then the new index of the encrypted character will be that index plus to handle a wrapper, right? Do you feel like you have enough to go on? Okay, get cracking. If you get stuck at all, just raise your hand, give me a question. Oh, the maybe type. So in order to look up an index in a character, you need to understand a little bit of something about, in order to look up a character by an index, or to look up a character for an index, you need to understand a little bit of the maybe type. So if I go, there's a function called lookup, I believe. find index. Which takes a function as its first argument that has a character and returns a Boolean, and so that's going to be a predicate. And then it takes a text and it returns a maybe int. And so in order to use this, you may have to do a little bit of understanding of pattern matching on the data constructors. So let's see, do I have that available in the prelude? Yeah. So maybe has two data constructors. One is just, which takes a just and an a value, where a can be any value, and the other is nothing. And so if I wanted to look up a character in symbols, and I do t.index find index, I could do something like this. Let's see. Get my Caesar cipher in here. If you see something like that, you may just need to build or to reload GHCI. And if you get into a situation where there's like a lot of modules, you can always use the :m, and that'll kind of clear everything out just down to the prelude again. And then you can import just what you want. So now that I've got symbols available, I can do t.find index. And then here I need a function that accepts a character and returns true or false. So I could do an anonymous function like this that takes a C and says returns C is equal to C, like this. And then my symbols, oops. Boom, boom. And I get a just 28, right? And then if I looked for something that wasn't there, like I don't have a 7, then we get a nothing. You can also kind of shorthand this. Since the equals operator is itself a function, we can partially apply it like so. And then same exact thing as before, but just a little bit shorter. So really up to you what style you prefer. Now, to use this, though, we might run into trouble, right? Because if we wanted to say something like, let's say, this, let found, let index, we'll just do index equals. Now if we try to do something, because we're going to have to shift that index, right? And if we try to shift it by like 5, we're going to get a weird error like this. And it says no interest for num for maybe int. And the issue is that what we're trying to do is we're trying to add 5 to just 28 or whatever, which doesn't work. We've got to grab the 28 value out. And so the way that we can do that is with pattern matching on the data constructor. And so in our encrypt char, we can do something like this. So we can say, let maybe index equal t.find index. with that equals equals C now, so it's not hard-coded anymore. And then we can say add index takes adjust I, we'll add I plus key. Let's do this and call it new index. And then we can say new index. There's nothing we can really do. If we don't find the character, we can just return it as is. In, and then we can call new index, maybe index. I'm going to get rid of my type signature right now in the hopes that this can compile. Oh, we've got to t.findIndex needs one more thing, symbols. Okay, what did I do wrong here while I was? I just love this compiler. Okay, so we want to say if there's a new key, if we found something, then add it to key. Let's make sure that works. Otherwise, if we don't find anything, we could just keep it as is. There we go. Now, so This is just to demonstrate how we can unwrap that value there to get what we need. We can't, when we have a function that returns a maybe of something or some other kind of container or context type, in order to operate on the thing that's inside, you're going to need some kind of helper function. Which can be a little bit hard to intuit when you're starting out. Does anybody have an encrypt character function completed? Yeah? I see. So if you encrypt Z, you need to handle wrapping around. So see what you got. Very, very nice. Cool. Cool. So there's a couple ways you can handle the, well, there's probably several ways you can handle the wraparound situation. One is to get the length of the symbols and then check to see if it's out of bounds. And if it's out of bounds, do some arithmetic. Another way, that was just used here, is that Haskell has the ability for you to write infinite lists. And there's a function in the text package that does the same thing as replicated on a list. And so you can actually just make your list repeat forever. And the beautiful thing about repeated lists is that you don't have a wraparound problem.
Does it have a function that repeats it forever? Because I used replicate, which I had to give in an int for how many times that replicated.
There is one that will repeat forever. There will only be a side effect if you try to access the, so yes, a little bit. So there's two text types. There's the one that we're using, which is data.text, and there's another one, which is data.text.lazy. And so data.text.lazy will not load the handles essentially streaming and laziness differently than data.text. In most cases, again, just pick one or the other, and then when you run into problems, benchmark it and move from there. Getting too deep into the implementation details of these types. This will talk a little bit about it here. That it's a good rule of thumb in Haskell just to more or less assume that if you're not accessing the value or operating on a value, that there's not a ton of implications.
But if I were to implement it as is, basically all the examples would not work because they type against text, not the lazy version of it.
Yeah. But the API is almost exactly the same. So if you import qualify data.text.lazy as T, then in my experience, I've had projects where I've just flip-flopped them to see if there's performance improvements with either one, and it's just worked with both types. So there's some things that are different, but a lot of times you can get away with. Makes sense. You probably don't want to do that. Um, and then otherwise, don't do anything. And then I say I have my little thing to say if we're encrypting and we found a key, then add it. And if we're decrypting and we found a key, then subtract it. And then I have the definition for my shift character. And we say, if we have a successful lookup, use the index of symbols, and then we're going to handle wrap with new key, mode key of I, and we're going to get the length of the symbols. And here I could pattern match on nothing, but I wanted to be really explicit to say, if I didn't find something, I don't want to do anything with it. Let's see if and then we should be able to do something like this. It looks like we're working. So kind of just walking through this, again, particularly in these early examples, this in particular is an algorithm that I saw in Python that I just tried to copy over into Haskell, like as much as possible without trying anything. So it's kind of a really imperative, even though we are in Haskell, this is kind of a really imperative way of working, and it has some negative implications on both performance and also, I think, readability, because when we start reading our function, we get this shift character index. So we have to go all the way down here to read shift char just I. And then we have to say, OK, well, what is index? OK, index is going to be t.find index. OK, that's going to be a maybe. OK, so that if we find it, then we're going to walk through this. Then we've got these nested function calls. And we're not going to do it right now, but if you try to run something like this on, say, like an entire book or a lot of text, it's very, very slow. Yeah?
Just one thing, you seem to always use this mode, encrypt and decrypt, and then pass it through one function. Would it be better to just completely have two separate
Yeah. We could even do something like this. Like we could say encode character, and then we could say
It's just a question of design. What do you prefer and why?
neither of these are super my favorite anyways, so I don't have a lot of strong opinions about especially this early code that we're going through, just kind of demonstrating different ways of doing things.
Yeah, no, effectively you put it in one signature, whereas intuitively I would have put two different functions, completely different functions with different signatures. That's what I'm saying. I'm just wondering whether this comes from somewhere.
Part of what made me do it is that essentially everything is the same except for this.
Okay.
And so,
For symmetric encryption in general.
yeah, felt like. And then you could do something like this. So with currying, so we could say encrypt character, and we can seed it with the mode and the key. And maybe in that case, I probably would have preferred if I had reversed the order of the arguments as well, so the key came first. But in this case, it's just, I'm really just playing around. Please, don't take this very seriously, stylistically. Yeah, sure. I will write some code that I think is pretty decent throughout the course of this class, but we haven't gotten there yet. But yeah, but this does work. And the nice thing about it is we can now reap the benefits of basically just forgetting what that encrypt character function does itself, and we can write our fold and separating those concerns out at least. So for fold, and I'm going to actually put this let's do something like this. So we can do a little anonymous function here. And let's say this is going to be the result and the C. Oops. And then basically all we need to do is snock the result with a call to encrypt car with the mode, the key, and the C. And we can see that and then we should be able to say E equals oops. Oh, I referenced itself. And I've made
but it's just a map, right?
sorry?
I mean, entire entire construction of result, it's just the same as
Oh, I renamed it. Yeah, you could map as well. And map will actually be much better. But I also wanted to make people practice with folds because I feel like folds are a little bit more difficult to get used to doing. And fold is actually, in this case, closer to the Python algorithm. So it's also really imperative. And I wanted to go from like a very imperative way of thinking to a really declarative way of thinking, which is where we're going to be moving in a second. But yeah, that intuition that map is really what you want because it's a one-to-one in length and it's a transformation of the individual elements. Map is a much clearer abstraction. We'll end up with cleaner code as well. Oops. Okay, whoa. Tmux, I'm sorry. Okay, so we have oops. This is the perils of those very design decisions. Okay, but working once the environment gets back into a good spot. However, if we take advantage of, we can think about this problem a little bit differently and move away from this idea that what we're doing is manipulating individual characters by indices and into a space where we're thinking about transforming the entire data structure. One of those would be to take a look at map and mapping something over. And another thing is to think about actually what the core algorithm of this is, right? And so originally the Caesar cipher was picked by Julius Caesar, and the key was not a number, but it was a character. And so they'd say, pick the character B, and then the character B would mean that they would put two alphabets. So if the key B was chosen, then they would just start the alphabet with a B instead of a C, and then shift like this, right? And this intuition exists because of the fact that we know inherently that these characters are ordered, right? And there's a character that comes before, and there's a character that comes after. And can anyone think of a type class in Haskell that encapsulates that kind of thinking? Enum. Yeah. And the type class for enum is ord. Really is what. So if we take a look at the ord type class, ugh. And actually, enum is even better. Enum is what we want. You were right, I'm wrong. gives us the successor to a value and the predecessor to a value, and it has to enum and from enum that allow us to convert from a integer into the type and from the type back into the integer. So let's take a look at a way of doing this. So but if you don't have it, make sure to add it back in. I'm going to import qualified data.text as t. I'm going to import qualified data.text.io as tio. And we're going to keep, I think that the intuition of having a function to handle encrypting the character was good. We should separate those concerns. If we can solve encrypting one, then we should be able to solve them all. But instead of doing all this math, what we're going to do is, in the case that we get a character, we're going to just pick the next one. So so let's see how this works. Encrypt char A gives us B. It's pretty good. What about encrypt character T? Gives us U. What about encrypt character Z? That gives us that. What about encrypt character Z? That gives us that. So kind of an issue here is we've got some edge cases, but luckily we can solve those with just a little bit of pattern matching. Boom. Oh no. Which one?
The line you're on, you need an N in the second column.
And?
Second column, you need an N.
Ooh, thank you.
But now it's not the same as the previous one because it wrapped from capital or uppercase down to lowercase, right?
Yeah, we could do that. Yeah. And I'm not crazy about matching that exact symbol line. In fact, I think in some ways maybe this is a little bit truer to the cipher. And then we can see something like, okay, it's going to be break time. Sorry. Oh. Oops. Okay, good. Take your break.